So this is where we pick up what to do about that negative square root. In a previous video, we ended up solving this equation, worked it through, completing the square, and we got the vertex form, which is right here. Oh, yeah, where the vertex form is. We got the vertex form, we're able to graph it. And the vertex form is actually this. I took this guy and put it over there. So from this form, we're able to graph it, which is right here. This is our graph. This is what we ended up with last time. It crosses at 9. That's the C value. So if I were to add this 6 over to, add the 5 over to here. Oh, I guess it crosses at 6. Crosses 6. And then my vertex is 2, 2. However, notice it doesn't cross the axis. And that is because of this guy, the negative square root. So negative square roots plagued mathematicians for years. And then sometime around, I think it was like 12 or 1400, or realistically it was probably the Babylonians, thousands of years before that, but we today attribute it to a bunch of Arabic mathematicians around 12, 13, 1400, I forget the date. And they were doing stuff like this and came across negative square roots. And I forget the context they were looking at it, but the application applies for today, for modern math. So negative square roots don't really make sense. Now let's explain why. So let's back up and look at just a square root of 4. So square root of the number 4. Now what a square root means is if the area is 4, what are the lengths of the two sides? Well, the lengths of the two sides are the square root of 4. In this case, 2 and 2. Notice we can never have a negative area because negative 2 times negative 2 is 4, and these dimensions have to be the same no matter what. So we can never have a negative area in the real world, okay? However, if I have square root of negative 4, I can't have, this doesn't exist. This doesn't make any sense. I cannot have a negative area. So that brings us to this other realm called imaginary numbers or complex numbers. What they devised, and this is the accepted notation throughout, is something called I. So I'm going to erase this. Let's take a look at this one here. The square root of negative 4. Square root of negative 4, I can actually factor this. I'm going to factor this as negative 1 times 4. Okay. Well, I know the square root of 4. That's 2. That comes out as 2. So 2 times the square root of negative 1. Well, this was their stroke of genius. The square root of negative 1, they called I, symbolized by the lowercase I. So let me write that up here. Square root of negative 1 equals I. Okay. Now, the next step is, let's take a look at this. If I take something square root of 4 and I square it, what do I get? Well, orders of operation says parentheses. So it's square root of 2, or square root of 4 is 2. Now, parentheses exponent, so 2 squared is 4. Okay. We could have cut to the chase because the square root and the square are inverses of each other. One does it, one undoes it, like addition and subtraction are inverses, multiplication, division are inverses. Square and square root are another set of inverses. Because they inverse, they cancel each other out, and we can just go ahead and use that value in the middle. We call it the radicand. Not totally sure on that. So, the square of a square root is the number in the middle. I bring this up because of this. If I square root if I take this, the square of negative 1, my value, my answer is negative 1. Okay. We also know that square root, or root negative 1 equals I. Therefore, I squared equals negative 1. Okay? It's pretty valuable. Keep this in mind. I squared is negative 1. So I'm going to write that up here too. Those two things will allow us to go back and solve this equation up here. Now, I'm going to admit right now, complex numbers or imaginary numbers like this really opens up a can of worms. There's a lot of math that we can do now, and a lot of math that goes along with this. We're just going to skim the surface so we can solve the negative square roots, plus a couple of little things here and there while we're at complex numbers. So, my roots to that equation up there were 2 plus or minus square root of negative 2. Okay? 2, we know what 2 is, that's easy. Let's do this one right here. So I'm going to factor it. Negative 1 times 2. Now we have an answer for negative 1. That's I. So now it's going to be I root 2. So I root 2 is this whole side over here. So now my roots are going to equal 2 plus minus the square, let me try that over. The roots are going to equal 2 plus or minus I root 2. The plus or minus indicates there's two answers. So 2 plus I root 2, 2 minus I root 2. Those are our answers to this solution. Now this might seem funny. This might be one of these like eye rolling, hey Matt, why are we doing this? Okay. Complex numbers are a big deal. This is how we model and how we design, develop, and figure out things like cell phone towers. How does the electric signal, the electromagnetic wave go from your cell phone to the tower? How does a current and electricity travel down a wire, information travel down a wire? How does light travel down a fiber optic? All of that, all the math and the physics behind all that, a lot of it, tremendous amount, involves complex numbers. They are for reals. We use this a lot in the physics, math, science world. Today, we're just going to skim the surface. They do come up a lot. You gotta trust me with it. The most straightforward example I can give you is it's the quadratic floating up in space like this. Other examples, if you want to get crazy, is how light reflects off a surface, and looking at the math behind that, turns out there's imaginary numbers. Something as simple as light reflecting. It's imaginary, complex. So let's try a couple more of these. Okay, square root of negative 72. First I want to do is get rid of this negative sign. So negative 1 times 72. Okay, that can come out. So now we're at I root 72. Now we just need to do the square root of 72. Let's see, that's 36 times 2. Something like that, because 36 times 2 is 72. Square root of 36 is 6. And we have 2 left over. So we're going to have 6I root 2 equals the square root of negative 72. Okay. 6I root 2 is square root of negative 72. Another place that we'll see this, let's just talk about the mathematics and how we actually manipulate these things. Well, let's start with this, 3 plus 2i. This number up here, we call this complex. And by complex, I have a real part. And an imaginary part. Now, believe it or not, every number you've ever used can be written as this complex number. So the number 5, right? Number 5, you've seen your whole life. Count your toes and fingers, 5. 5 is also, can be written as 5 plus 0, I. In this case, it's the real and the imaginary. However, the imaginary is 0. It doesn't exist. It's gone. Multiply by I, 0, it's gone. Okay, so it's just 5. When we do the math of these guys, is we add the real parts and we add the complex parts. So addition by this, I mean complex, complex, real, real. By this, I mean, if you're doing addition, subtraction, you just add the real parts, add the imaginary parts. So let's try this. 3 plus 2i, and I just put parentheses around these, make my life easier. And then 4 minus 3i. So, real, real, complex, complex. These guys come together as 7. The wrong one. These two come together as negative 1i, or 7 minus negative 1i, sorry. 7 minus I. This here, I just added them up. Easy peasy, okay? Multiplication is just like multiplying factors, multiplying parentheses. So let's go back to 3 plus 2i times 4 minus 3i. I think that's what we just had, right? I want to multiply these together, and we use the square. 3 plus 2i, 4 minus 3i. Okay. 4 times 3, 12. 4 times 2, 8i. 3 times negative 3 minus 9i. Negative 3 times positive 2, negative 6i squared. I times I is I squared. So let's go ahead and rewrite this, simplify this out. 12 plus 8i minus 9i minus 6i squared. 12 plus, minus. 12 minus 1i minus 6i squared. Are we done? No. I squared is negative 1. I squared is negative 1. So this guy here goes to negative 1. So now we have 12 minus 1i. Now this is negative 1, so it's negative 6 times negative 1. 12 minus 1i plus 6. Hey, check that out. We just took a complex number and by squaring it, we uncomplexed it. That's a big deal. 18 minus I. Here's my answer right there. Okay. Division is the same. Okay. Let's try another one. Let's try this. I want to do 3 plus 2i times 3 minus 2i. Nine, 6i minus 6i minus 4i squared. 9 plus 6i minus 6i minus 4i squared. Let's go ahead and simplify this. Positive 6, negative 6, those cancel each other out. So then I have 9 minus 4i squared. I squared is negative 1. Negative 1 times negative 4 is positive 4. 9 plus 4 equals 13. Hey. There's no complex part. We have now eliminated the complete complex part. This here, this is called the complex conjugate. I'm not sure we're going to do too much with that, but while I had the can of worms open, I figured I'd throw it at you. The big part is, by multiplying a complex number by its complex conjugate, we can eliminate the imaginary or complex part. See? So this is supposed to be plus 0i. That's the question mark. This guy just lost. Okay. One last piece, complex numbers. How do we graph these? There's a pretty interesting YouTube on graphing these things. Graphing X, Y, and complex. I'm not that good at drawing with chalk, but I can give you a little bit of a rundown. I'm going to call this axis real. This, okay, and the plane going in and out of the board to be real also. And I'm going to call this axis imaginary, just called I. Okay, so real and imaginary. So let's take the number. Hey, I like 3 plus 2i. 3 plus 2i, this complex number. This will be represented up here. So real is this complex part. This is 3 parts. So 1, 2, 3, right there. Then I got 2i, positive 2i, 1, 2. There you go. 3 plus 2i. If you remember back to our physics days, 3 plus 2i sure looks like a vector, doesn't it? But that's what it is. It's that line to that point right there. That's a 3 plus 2i. Let's try another one. How about 2 minus 4i? So 1, 2. So we're over here. Okay, that's 2 minus 4i. Now, just like in vectors, if I were to add these, I could add them either in the mathematical world, which we did a minute or so ago, or I can do vector addition. So let's take a look at that both ways. So 3 plus 2i and 2 minus 4i. You got 5 minus 2i. So my resultant vector is that, 5 minus 2i. So to do this up here, so I want 5 minus 2i. So hold tight, we're gonna come back to this. To do this over here, I'm gonna make a parallelogram. And the diagonal of the parallelogram, so this red line and this one over here, this white one and this one down here, those are parallel. This right here, this resultant, should be 5 minus 2i. Let's check our work. Let's see, 1, 2, 3, 4, 5. Yeah, that's reasonable. I'd say that's 5. And then minus 2. 1 minus 2. Close enough. So right here is 5 minus 2i. So what we have seen, a lot to this lesson today, is square root of negative numbers are doable. Square root of negative 1 is I, and if we square the whole thing, negative 1 is I squared. We can factor out the negative sign, which we did, like right here, factor out negative 1, then we just have I root 2. There are some other little things that come up with I. And sometimes I feel like these are just kind of like stupid human tricks, just like who cares? I'm not sure the application in the real world. Maybe a complex math has them in the long run, but I don't know. But we often see them come up in the mathematics world or in the textbook world, but I want to show you at least 1 or 2 of these. So what is I to the 17? You don't know. Well, I don't either, but we can figure this out. One of the things I know, here's what I do know. I know negative 1 is I, and I squared is negative 1. Okay? So, let's see. I 17, back that up. I'm going to factor this out. I to the 1 times I to the 16. Okay. And let's go off this I to the 16 one here. I to the 16 can also be written as I squared to the 8, right? Because when you multiply these out, it's 8 squared, 16. So I squared is -1. So -1 to the 8th power. If you remember your exponents here, -1 to the 8th. This here equals the number 1. So let's not forget this guy up here. We have I times 1, it's actually I to the 1, but I times 1 equals, oops, that's supposed to be an I. Take a look at what I did. What we did is we factored out the 1. So we had I to the 1 and then I to the 16. The 16 here, we broke down to 2 to the 8th, 2 to the 8th, which is still I to the 16. And I know I squared is -1. And I know -1 to the 8th is +1. Okay, so that takes care of this whole side. So that's just going to be 1. And over here, I to the 1 is just I. I times 1 is I. Negative numbers are more complex than even numbers. Let's times I to the 64. Ugh. I do not want to do this by hand. I don't want to go I 64 times. So instead, how about I squared times 32. 2 times 32, 64. And I know that I squared is -1. And then bring this guy down, -1 to the 32. Something to the positive power will make this a positive. The answer is 1. Okay. They're not always like this or like this, but the trick is to factor out an I or an I squared. So eventually you have an I squared in here to get a -1. Your goal is to get a -1 somewhere in the equation. Get a -1, all your worries go away, and your answer is going to be I, 1, -1, or -I. Those are the typical answers you get for an I problem like this.